This is a production of Cornell University.
So this actually sort of segues right back into that the pot experiment. But managing these plant nutrients, you sort of have to think about, well, where are we getting these nutrients? Okay? Certainly we can get them from organic sources, but we also can get them from inorganic sources, and we can get them from manufacturer sources versus natural sources. Okay? Fertilizer manufacture and use does not create nutrients. Okay? They're basically harvesting and concentrating. Okay? Now, when you say manufacturing here, most of us think of sort of the petrochemical industry, but you can certainly imagine this from sort of an organic waste management system as well. Vermicompost is a really good example of this. Composting in general is a really good example of this. When we went out to the waste facility, the waste compost waste facility, you guys remember the size of those windrows when the stuff came in? They were rather large. You know, within 6 months they were rather small. Well, what's going on? We're blowing off a lot of CO2 is being blown off. In essence, we're concentrating material. Now, granted, there's ammonia and there's other things that are being blown off as well. But in general, we're looking at a concentration. Okay? We then take that concentrated material and then put it back on our fields. The same thing is happening with the petrochemical system, you know, the industry. You know, we're looking at basically taking some material and concentrating it and then transferring it and putting it on our fields. Okay? Animal manure, green manure, compost, they contain nutrients that are taken from the soil. Inorganic fertilizer are basically mining enriched deposits. It's all about concentration of those nutrients. Okay? Therefore, fertilizer, in essence, is a non-renewable resource, in a sense, because in all cases, we're basically mining. Now, there is one exception, but in a sense, this is also a non-renewable resource, and that has to do with nitrogen. With nitrogen fixation, basically, we're going to be taking nitrogen from gas, and using biological chemical fixation, we basically take that nitrogen and convert it into ammonium or ammonia or NH2, some variant of that. Okay? But in all of those cases, there is a large energy cost, whether it's heat or whether it's ATP. Question?
What exactly is green manure?
Green manure is basically a cover crop or something like that I'm cutting and throwing into the system. It's not literally green manure. Yeah. Okay. Okay. Questions? No? Okay. So let's talk a little bit about where these nutrients come from. Okay. The first one is nitrogen, and we always start with, not always, generally we start with nitrogen because it's usually the one that's most extensively needed or used. It's usually the smallest slat in the barrel. Okay. It's also the one, besides carbon, hydrogen, and water, that is used in most abundance. Okay. Nitrogen deficiency is normal. Okay. It's common and it's normal. And plants are used to this. Okay. Few soils can sustain multiple harvesting without some sort of nitrogen amendment. The crops are just sucking it up too much and taking too much of it out. Okay? Phosphorus deficiencies are pretty common there as well. In fact, I'm not sure if this is correct at this point, but about 70% of agricultural soils, not in New York State, but about 70% of agricultural soils are deficit in phosphorus for plant uptake for some period of time. Okay? Questions on that one? I thought I saw a hand. No? Potassium, sulfur, zinc deficiencies are common, but they're probably, even with these deficiencies, they're probably not the limiting nutrient. Usually it's usually nitrogen and in some cases phosphorus. Okay? Oh, I thought I had another slide here. Oh, I do. I skipped sorry. I put the slide in the wrong spot. Other nutrients, iron, boron, molybdenum, manganese, copper, magnesium and manganese. Deficiencies are less common, but they are out there. Okay? Chlorine, cobalt, and sodium, these are really rare deficiencies, but they do happen as well. And then calcium, its deficiency is rare, but calcium's kind of interesting. When calcium is in excess, calcium can actually suppress other problems. obviously, acidity, I mean, you start throwing calcium in the system, you're going to be raising the acidity. It's basically a liming reaction. But you also can potentially be dealing with reducing issues of sodicity and salinity. This is where my slide was supposed to be. We're going to skip over. The transition here was basically, OK, well, we know what these nutrients are. How do we, in fact, make decisions about fertility? OK? Well, let's take a look at a number of different crops. Okay, and this is a wheat, an alfalfa, and a tomatoes, sort of a variety of different crops here. The take-home story, in a sense, is from a farmer's perspective, is how much yield are they going to be taking off that farm? Now, this is probably a low yield for grain at this time, but just imagine that these are the numbers. Okay? Now, from a fertility management sense, what do these numbers actually mean? Well, when I harvest this 6 tons or this 20 tons or this 20 tons, I'm going to be taking nutrients with me. Okay? Now, if I'm taking a wheat, I got 6 tons, I'm basically taking kilograms per hectare, 120 kilograms of nitrogen, 30 in phosphorus, 30 of potassium, 25 calcium, 15 magnesium, and 5 sulfur. So in essence, this is removal, this is loss of nutrients from my system. So you have to think about what you're growing to give you an idea about the yield, and that yield, what does that yield actually reflect? Okay, now from a farmer's perspective, think about the application rates. Now these are not the exact same, and they're sort of out of order here. Okay, so field crop we can think of as a wheat grain, vegetables we can think of as tomato, and alfalfa is alfalfa. Okay, this is the yield. This is what I'm losing. Now from a farmer's perspective, I need to make that up somehow, a grower's perspective. Well, depending upon my crops, this is what I'm going to apply. Again, kilograms per hectare. Field crops, about 100 kilograms of nitrogen, 7 phosphorus, 4 potassium. That seems to be less. Why?
Because some of the residue is staying.
Some of the residue is staying, but these numbers reflect what's leaving. It's not the entire, it's not the entire plant, it's just what's leaving the field.
Those nutrients are still in the soil, but they won't become available at the rate that you need to crop again, so you have to add some to supplement what's coming into the soil solution.
In many cases, that's going to be the answer. So the answer was, those nutrients are still in the soil, but they're not necessarily at the rates that are available, or they're not necessarily at the rates that the plants need. Is that basically what you said? Okay. And part of that is correct. But part of that also has to do with what other type of organisms are in the system and how is this material getting into the system. Okay. If there's organic matter in the system, there's still stuff there. If there's minerals in the system, there's still nutrients there. There's still stuff there. Okay? But I need to be able to supply the nutrients based on the lifestyle of my plant. Okay? And a good example of that one is actually looking at alfalfa. If we look at alfalfa, nitrogen application rates, alfalfa leaving the system, look how much nitrogen is leaving the system. Yet, me as a farmer, am I applying any nitrogen to my alfalfa crop? Now that has to do with my crop. What is my crop? It's alfalfa. What has alfalfa the ability to do? Or not necessarily alfalfa, but something that's in a symbiotic relationship with alfalfa. Nitrogen fixation. Put alfalfa into the system. I don't have to add any more nitrogen. If there's no nitrogen there, it's not a big deal because they can do nitrogen fixation. Alfalfa will go into my plant, and I don't have to worry about it. Does that make sense? So thinking about what your crop is, what you're harvesting, and what's leaving the system basically is telling the farmers what I need to put in the system based upon what crop I'm using. Makes sense? Yeah? Okay. So let's go back to these fertilizers again. Okay, where do these fertilizers come from? Okay, there's natural sources as well as manufactured sources. Natural sources can be both organic as well as inorganic. Organic sources are often what we think of as biomass type of amendments, manures, mulches, composts, that type of thing. But we can also have inorganic sources that are also natural. Example here is rock phosphate. It's not like we're manufacturing rock phosphate. This is a geological material. Okay? Now we mine it and we can process it to make it more concentrated, as we talked about before, but it's still a natural source. It is inorganic though. Okay, we also have, hey, what's going on here? We also can have manufactured materials, and nitrogen is the classic one of this case. And in soils, plants, animals, ultimately comes from the atmosphere. So when we're manufacturing it, we're basically taking it from the atmosphere, and this is the Haber process. Okay, this Haber process, from a manufactured sense, we're basically taking N2 gas with hydrogen, we're putting it over a catalyst under heat, and we basically make ammonia. Okay, the heat and energy here basically comes from coal, petroleum, any kind of hydrocarbon type of thing, anything to get energy. Okay, we can then take this and under pressure with low temperature basically make ammonia. Okay, and we can take this, or say liquid anhydrous ammonia. So we basically take this ammonia and concentrate it. It's not what we're making. This is making the ammonia. This is concentrating it. Okay. Worldwide, nitrogen fixation, about 50% of it's biological, about 50% of it is industrial. Other nitrogen fertilizers, so we take that ammonia, throw it under oxygen, we can basically make nitrate, turn it liquid. Okay, a lot easier to transport than a gas. Okay, if we wanted to concentrate it, we can put it with ammonia, we can put it with lime, we can put it with calcium, make a urea, we can actually put it with phosphate, make an ammonium phosphate, all different kinds of things. The truth is, all of these are basically easier to handle. All right, all of those are, that just happened. Did I totally miss something while you guys look at the screen and I was talking? All right, whatever. Luckily, we only have 5 minutes left. All of these basically can get concentrated, and they're all generally easier to handle than ammonium. Okay, ammonia's gas, i.e. that's the big issue there. All right, question.
So they actually make ammonia, or they actually make urea from ammonia. They just don't use.
They don't use the urine, yeah. Because it's easier. I hesitate to say this. I can tell you the party line. It's easier to handle and easier to deal with if you manufacture it rather than harvesting it from all these cows across the world or wherever sources. I'm not necessarily sure I buy that argument, but I do buy the argument the way the system is set up right now, because of logistics and supply lines and things like that. I do understand that argument. But I mean, we can get urea from natural sources, but right now the system's set up. Now I can complain. In fact, I think this is wrong, but that's the way the system's set up right now. Okay, I have 2 more slides that I want to hit before I let you guys go free. This was where we were. The last sentence I basically said was, because of this transformation from that ammonium, we're basically making these things much more easier to handle. A liquid is a lot easier to handle than a gas. Okay? And also it affects, in a sense, it's not just sort of transportation, but it also has a lot to do with how you actually apply it. You have to have specialized equipment, and we'll talk about this later, I think on Friday. You also have to have specialized equipment to get gas in your soil. It's not like you just spread gas. And when I talk about gas, I'm not talking like gasoline. I'm talking like gas. Okay? You can't just sort of spread gas on your soil because it will just volatilize off. Okay? So you actually have to have very specialized equipment to be able to use gaseous forms. Okay? Phosphorus fertilizer, the main industrial source is rock phosphate, which is basically apatite. It's mostly like Florida and things like that, where we're literally mining rock. Okay? They then process this to grinding, which is what we basically see as a rock phosphate. We don't get the rock itself. They grind it up. But we also can mix it with sulfuric acid, making superphosphate, or we can put phosphoric acid in and basically turn it into triple superphosphate. I can barely say that. But basically what you're looking at here is sort of a 3% phosphorus content, This one says 9%, and this one you're looking at like 20% phosphorus content in that material. Okay, so that would be an NPK of potassium fertilizers. These are another primarily a mined material. We're looking at sedimentary deposits. Sulfur, we're basically looking at gypsum, which is a mined material. This is fairly abundant. This is also mined from sedimentary material. The other good thing about this is you're getting multiple nutrients on this one, and it's fairly soluble. Okay. Elemental sulfur is another source. This is fairly insoluble. It's an oxide, but in soil, when you put it into with oxygen, it basically turns into a sulfate. Now the problem with this is that you potentially will get the hydrogen with it. This is a lot of what you see with, not the elemental sulfur, but with the sulfides, this is a lot of what you see with acid mine spoils, as well as dredged material. The sulfur comes up as a reduced sulfur, gets in the presence of oxygen, it becomes oxidized, and it basically turns into sulfuric acid. Okay? That sulfuric acid will drop the pH of your soils pretty precipitously. Now, this can actually be a management goal, though. If you have a really high pH soil, you might in fact want to use this sulfur, not necessarily for the sulfur, but for the protons to drop the pH of your soils to a more ideal zone for nutrient availability. Does that make sense? Yes, kind of? All right. Then phosphorus. We also have organic fertilizers. This is the last slide before I'm going to set you guys free. Organic fertilizers basically are derived from plants. Ultimately, they're derived from plants, even if you're looking at a bone meal or a blood meal or something like that, because those animals are basically surviving off of plant life. Okay, so unprocessed, obviously, things like leaves, clippings, things like that. We also have animal processed stuff where they're taking the plant material and we're looking at things like manure, bone meal, seaweed sludge, all that kind of stuff. And then we also have microbial processed stuff where we're looking at composts. Okay, vermicompost is sort of a blend between the two. Okay, the vermicompost is an animal, but there's a microbial linkage there. Okay, does this make sense? Okay, the take-home message from this slide and some of the previous slides is fertilizer management and fertilizer manufacturing is really all about concentration and moving those different pools to where you want.
This has been a production of Cornell University, on the web at cornell.edu.